nice verse I found from Shakespeare in some biography of Professor Raman. It says, turning the accomplishment of many years into an hourglass for the which supply, admit me chorus to this history, who prologue like your humble patience brave, gently to hear, kindly to judge our play. Now you may wonder why we should be shown here, but in a strange way there are many thoughts here which have bearing on these experiments. In our case, not accomplishment, but just effort to assemble all this over many years. Some of the experiments we set up some 20 years ago, and others more recently. And I will hopefully talk for an hour, not more than that. And also an hourglass will figure some of the experiments. And most important, these experiments all have been tested, but already one doesn't seem to be working. And I hope the others will behave themselves. If they don't, I hope you will bear with us. So just a little bit of motivation and then I'll show experiments. Maybe summarize. Joel Walker, who is write the amateur scientist column in Scientific American, has written a foreword to a book saying the primary reason scientists become scientists is that science is a thoughtful form of play. It's fun to see an arrangement of common items behave in a surprising way and try to figure out why it acts. So most of the experiments involve very simple equipment. So you can all try it at leisure and then figure out what's happening. Before going on, I would also like to share with you this thought, which has also been echoed by chemical engineers such as Felder and Woods, that the traditional form of lecturing is not very effective. We have to make the student participate actively. So, for example, Mr. Patsadi, who is a philosopher, has written, knowledge has to be drawn out of the students, not thrust into them. So, a liberal use of question and answer sessions would be effective. So, I will ask questions and I hope some of the students here will try to answer. If you don't know, it's all right. We will continue. The first experiment, I just titled it after the biblical story of a small person taking on a giant Goliath. And but David is armed with a slingshot. So the equivalent of that is this experiment taken from the book by Earl. There is some weight here. In this case, used printer cartridge and something much lighter, say paper clip. Now we need a support. And, I hope it works. See, when I leave the pin, it can balance a heavy weight, even though it's very light. So the slingshot here is what? Can you guess? What is it which helps?
Friction.
Yeah, friction. And the friction increases with the number of turns exponentially. So even a light object can balance a heavy weight. But there is one variation of this that doesn't quite work like that. So now suppose I leave it. Why doesn't it balance now? Same friction is there. So some of the students can tell what will happen. I'll do it once more. See if I hold it like this. Next time, I just hold it this way. So what is the difference between the two? Huh? Distance. I can keep the same distance. I'll release like the same way as before. Yeah, but why are there no loops in this case? That's the question. Normal force is greater. Why should it be? The first time I'm giving seminar in circular seminar halls. Please forgive me if I don't face some of you.
Maybe related to your question.
Yeah, in some sense. See, when I release it like this, the pin is falling down because of gravity, also pulled towards the pen because of this weight. So angular momentum is generated. So as the length of the string between the pen and the flip become less, to conserve angular momentum tries to go faster, so it winds around. In this case, it is mostly translating because there is not much angular momentum, almost parallel. So then it falls down. So this kind of experiment is so simple, it can be shown at school level and also. Now you may wonder how this comes about. Frictional force increases exponentially with number of turns. At the end of the seminar, if somebody wants, I can show you derivation given by a very simple force balance. Okay, now we will try the next one. For that, Raghuram might need some help. This is a very simple experiment using mineral water bottles. We have sand here, and in this one I am going to fill water. And there are two holes where this paper is. Two holes. Similar holes here, but for operational reasons they are much smaller, maybe a millimeter or so. These are closer to 10 mm, little less. So now we know that, can you use the board? So suppose we have water, we know that the lower jet will go further away. But suppose we have sand. So can you guess how the jets would look like? Will they be parallel or will they intersect? What is your guess? Okay, we will try the experiment. Just bear with it for a little while till we remove this. Just remove the blocks. Yes. Okay, I just hold it. You can see. And, they also can see if you turn it. That's it.
This side, please.
You can see roughly parallel jets. We will continue like this.
You stand, is it?
This side. Okay, and you will notice the free surface will become inclined. With water, we don't expect it to be flat. So again, the students may like to say what will happen in here. Oh, I kept the pens in there, but I lose the other one. Okay, this behavior is related to another experiment due to Phillips, which I will go and come back to this. Okay, before I go further, let me say that wherever you find stars, these are all the people who helped me in setting up various experiments. Some were students, some regular students, some of my colleagues, and so on. So let me go. Okay, I will just tell you. Yeah, this is the one. This is a nice experiment done by Phillips 100 years ago. This is a tube with sand, sand. Okay, and the bottom is closed with tissue paper. So if you try to press on the sand, however hard you press, the experiment has failed because it has not been fixed properly. But the tube is longer and it's fixed properly here, then the thing won't tear because the force is not transmitted down. What happens is, I'm sorry, the flow is clean it up. Plot the normal stress on the wall then versus the depth. Measurements show that it levels off to value it scales with the width of the container, not the depth. So regardless of the depth, if you go deep enough, normal stresses are independent of the height. And that's the reason why if you make a hole here or here in the asymptotic region, the flow rate is the same.
Why is no stress?
Because of wall friction. If there were no wall friction, then the variation of pressure in the static column would be hydrostatic. So we can easily write a force balance. If you take this element, so we